Okay, so I think it's okay. I think we can go ahead. Okay, so today it's my pleasure to welcome Anders Peterson to give a talk to us today. If please mute yourself if you just joined here. I'll take care of it there. Any case, back to what I was saying here. So we're pleased to welcome Anders Peterson for today's ARC seminar. Anders is a computational mathematician working in the computing directorate at the Lawrence Livermore National Laboratory. He received his PhD in numerical analysis from the Royal Institute of Technology in Sweden. He also holds a Doctor of Science degree in hydromechanics from Chalmers Institute of Technology in Sweden as well. He's worked on a variety of projects with various applications over his career. Most recently, he's been working in characterization and control of superconducting quantum devices. Currently, he serves as the Livermore PI for the earthquake simulation project within the DOE exascale computing project. That sounds actually very interesting. And also serves as a Livermore PI for the DOE ARC project team. So with that, I will pass it over to you, Anders, to begin the talk.
All right, thank you very much. Now I'll let me share my screen here. Thank you for the kind introduction. So today I would like to talk about a software package called Quandary, which is written in C++, it's open source, and it does optimal control of open quantum systems utilizing high performance computers. So this project has been going for about 2 years now, and this is joint work with Stephanie Gunther and Jonathan Du Bois in Livermore. So, optimal control techniques can be used to improve the speed and fidelity of a number of fundamental operations in quantum computing. In this talk, I'll focus on applications to superconducting quantum devices, where control is implemented in terms of microwave pulses. I will focus on two important functionalities that are essential to implementing any algorithm on a quantum computer. The first one is state preparation, which is needed for initialization, and it's also an essential component in error-corrected schemes. Here we need fast and accurate reset of qubits to the ground state or some other well-defined states. Second essential functionality is the realization of unitary gate operations, such as the single and two qubit gates in a universal gate set that is used in many commercial systems, or the realization of larger multi-qubit unitaries, such as Toffoli gates or generalized swap gates. Such larger custom unitaries are also needed in Hamiltonian simulations, where the quantum device simulates the evolution of some other Hamiltonian system. So, as we all know, issuing control pulses to a quantum system implies that the quantum system interacts with its environment. Such interactions can be modeled by solving a master equation governing the density matrix. So current open source packages such as Qutip and Krotov can do this, but are limited to rather small quantum systems because these codes only run on shared memory platforms and with very limited parallel scalability, mostly achieved by allowing independent problems to run concurrently. And also I'd like to mention, in general, if you have any questions, please feel free to interrupt and ask them as we go. I think that's better. Maybe Greg can moderate them if you put the questions in the chat.
Yep, sounds good.
So to mitigate shortcomings of the existing simulation codes, we developed Quandary. So as I mentioned before, it's written in C++ and it was born parallel. So it's designed for running on distributed memory HPC platforms with thousands of compute cores. The functionality of Quandary includes the ability to simulate the dynamics of a given open quantum system based on Lindblad's master equation. The Quandary can also implement adjoint-based optimal control to design the control pulses to realize conditional and unconditional state preparation, as well as unitary gate operations. So as I mentioned before, Quandary was born parallel, and it utilizes the MPI library. MPI stands for Message Passing Interface, and that is used for efficient execution on large HPC platforms. So we've implemented several levels of parallelism in Quandary that allows us to scale and distribute the calculations over thousands of compute cores. And I also like to mention that Quandary is open source and it's available on GitHub. Whoop. I'll turn on my laser pointer here. And if you go to this website, you can download it. We're also very interested in collaborations, and you're welcome to contribute to it. Okay, so diving into more details here of what Quandary does. It implements a rather general computational model of open quantum systems. So we consider Q-coupled subsystems, each model with n sub q energy levels that can be different for the different subsystems. And we're represented by a density matrix rho here that is of size n by n. And this capital N is the product of the number of energy levels in each subsystem. So as we know, this capital N will grow quickly with the number of subsystems in the problem. So the evolution, we assume, is governed by Lindblad's master equation. So here it has two fundamental components. This first bit here is the unitary evolution, governed by the Hamiltonian H. And then the second piece here, L of rho, includes the collapse operators that model the non-unitary evolution. So Quandary implements this form of the system Hamiltonian. So the Hamiltonian has two pieces. It's a system Hamiltonian and it's a control Hamiltonian. So the system Hamiltonian is assumed to be independent of time, and it captures generally, we model everything in a rotating frame. So we have terms taking into account the detuning, the anharmonicity, and then we have implemented two types of coupling terms. So you can either use a cross-curve term, or you can use a Jaynes-Cummings coupling term, or you can use both if you wish to. The controls Hamiltonian is where all the action happens. That's the time-dependent term, and it has this general form. There's an unknown time-dependent function, complex function f sub q here, the action, the lowering operator, and then it's conjugate that acts on the raising operator. And one thing that is different in Quandary from other codes is that we parameterize this function f sub q using quadratic B-splines with carrier waves. And they have this form that we see in this formula. So so we can have a number of carrier frequencies, and they are picked such that resonances in the system are triggered. And then it multiplies this form here, where these alphas are coefficients, complex coefficients that multiply B-spline basis functions. So these B-spline basis functions, they're illustrated here on the right. So we have, in this case, 3 of them. We have a blue and a green and an orange. And by varying the amplitude of each one, you can model more general, complicated pulse forms. And then when you multiply everything by a carrier wave, you might get something that looks like so. So with very few coefficients, you can model rather complicated waveforms. And one essential feature of this is that the number of control, or the dimension of the control vector, the number of controls, is independent of the time step in your Lindblad simulation. So it's possible to run first at a coarse mesh in time to do preliminary calculation and determine preliminary values of all these control vectors. And then for a more accurate solution or simulation, you can refine the time step without doing anything to the control description. Okay, so another feature of Quandary that might be slightly different from what's usually done in these types of simulation codes is that we employ a Runge-Kutta time-stepping scheme to solve Lindblad's equation. So to do this, we actually vectorize the equation. So that means that you take the density matrix and you just stack all the columns in the density matrix and put it in a vector Q that is now with size n squared. And then this whole operator on the right-hand side, you do the appropriate manipulations and you get the super operator that we call M of t. This is a matrix of size n squared by n squared that is very sparse, and it operates on the vectorized version of the density matrix. So this is a standard form of an ordinary differential equation, or ODE, which we then solve using a Runge-Kutta time-stepping scheme. So yes.
Could I ask a question? Sorry.
Yeah.
When you get to your M of t, shouldn't there be M also dependent on rho? Because the right-hand side of your ODE, L of rho, the collapse operator depends on rho.
Yeah, so all these things are inside M.
Right. So M is not just a function of t, it's also a function of Q.
No, this is a linear equation.
Okay, L is a linear operator.
It's linear operator of rho.
Good,
Yeah.
thank you.
Yeah. Right. So given initial state Q of 0, which is the vectorized version of the density matrix initially, we can use a Runge-Kutta scheme to calculate what the state is at the final time, capital T. So we use the implicit midpoint rule to do this. It's a very nice scheme, has nice properties. Because the evolution is highly oscillatory, we believe it's important to use a symplectic integrator. And it also happens to be symmetric, which is very handy when you want to compute things like the gradient of an objective function. It is second order accurate in the time step. So to give some examples of what Quandary can do, the what we call the simplest optimal control scenario is conditional state preparation. So what we mean by that is given a known state of the system, we want to find control functions such that we drive the system to a target state. So this is an ODE constrained optimization problem where we want to minimize the subjective function that we call J that depends on the target and the evolved density matrix at time capital T. under the constraint that this density matrix at the final time actually is a solution of Lindblad's equation with that initial condition. So in our work, we have implemented two different objective functions. The first one we call the Frobenius one. It's the Frobenius norm squared of the difference between the evolved density matrix and the target density matrix. So this is very easy to understand that, and the only way the evolved density matrix can get to the target is if it equals the target, because this is a norm. Another objective function that is used commonly in the literature is based on the trace overlap, and it's based on something called the fidelity. So the fidelity of the evolved state here, when the target is pure, satisfy this formula. So you take the product of the two density matrices and you calculate the trace, and you take 1 minus that. So this trace is between 0 and 1, and you take 1 minus that. So you want to minimize this trace. It's possible to show that these two objective functionals are related, and the difference between them comes from something called the purity of this evolved state. So that's how close this state is to a pure state that can be written as a outer product of a state vector. Okay, so to solve the optimal control problem, we do iterative gradient-based optimization. So we apply quasi-Newton updates for the control vector. It's of this basic form. So we need to compute the gradient of the objective function at the current value of the control vector. We precondition it using this LBFGS technique to approximate the curvature information that would otherwise be in the Hessian, and then you update to get a new control vector. And then you iterate until this whole thing hopefully converges. So we employ the first discretize, then optimize approach. So first we discretize the objective function in time, and then we use algorithmic differentiation to derive the formula for the gradient, and then we implement that. So the advantage of this is that the gradient of the discretized objective function will be exact for any finite time step. The other approach of doing this is to first optimize, then discretize, and then you can pick any discretization scheme for computing the objective function, and then another one for the gradient. And that, in general, is only guaranteed to be consistent in the limit as the time step goes to 0. So that can lead to some convergence issues. Right. So this conditional state preparation can be exemplified by a simple problem where we have 3 coupled qubits in the ground states, and then we want to drive them towards this maximally entangled GHC state of this type. And here we see that we show the optimization history. So the purple line here is the objective function. It goes down very nicely to a very small level, and then also the gradient of it here in green goes down to a very small level. So here we can say with certainty that we have found at least a local optima of this optimization problem. Also here, in blue, we show the fidelity of this, and it goes up towards 1. So that means that also the trace fidelity, which is 1 minus 1, is close to 0. On the right, I show the control functions, and also the expectation of the energy level of this. So in this case, the expectation of the energy level of this system would be 1/2. So it's 0 here and it's 1 there. So it's the average of that. Right. So the next problem that is more difficult is the unconditional state preparation problem. Then you don't know where the system starts, illustrated by this cloud here. So it can be anything. And you want to find control functions that drive it still to a well-defined target, a pure state target. So the most direct way of doing this is to consider a basis of initial conditions here. And you span all those elements in the basis. And if you drive each one of them towards this target, then any linear combination of it will also end up at the target. The problem with that is that when the size of the state is large, you get a lot of basis states. You get n squared, or maybe n squared minus 1. I'm not quite sure, but it's many. So it can be much more complicated or expensive to evaluate the objective function. Nevertheless, it can be done, and this is the objective function we use, which is just the average of the individual objective functions for each of these initial conditions. So to avoid having to solve n squared Lindblad equations for evaluating the objective function in each iteration, we have found a way around it, and we've designed a specific objective function that avoids this. So here we consider our objective function to be the trace of this number operator times the final density matrix. So this is sometimes called the observable, and it has this form. It's just the diagonal matrix, and the first element here is 0. This thing measures the expectation of the energy level at the final time. So here the interesting thing, and I've just state the result here. If you want to see how we came to this, you can look in our paper that recently appeared, stated down here in AVS Quantum Science. But we found that by designing an ensemble state, which is of this type, so here it's an average over all our basis elements that each are pure states. Because this objective function is linear in the final time, density matrix at the final time, you can you can get away this problem of having to solve n squared problem. So you essentially move this, because this j is linear, you can move the sum inside this parenthesis here, and instead optimize with respect to one ensemble state. And that only requires one Lindblad solve to evaluate the objective function in each iteration. So here's an example. So here we have 2 qubits that are coupled to readout cavity. And I should say that this whole reset process, it works because there is one part of the system here, the cavity, that decays much faster than the qubits. So when the qubits had a shorter decay time, a common approach to this was just to let the system wait, leave it alone, and then it will eventually decay towards something that's close to the ground state. But here we want to do something much faster. So we couple it to the readout cavity that decays much faster. And we construct this ensemble state, and we optimize the control pulses to drive the whole system to its ground state. So On the left here, it's a rather complicated figure, but it shows what happens for various initial states when you apply these pulses. So this is a 5 microsecond pulse, and the red curve here is the evolution of this ensemble state, and it eventually goes down to something that is of fidelity 99.2%. What's interesting here is that if you start in other states, they all seem to coalesce and merge around about halfway through and then evolve together. Another interesting thing to look at is the von Neumann entropy. And here we scaled it so the maximum value is 1. And for this ensemble state, it starts with 1 and it decays monotonically towards 0. And if we try a couple of other initial conditions, we see because they start as pure states, they start with entropy 0, quickly grows, but it always is bounded by this ensemble state. It's kind of a worst case scenario. So this shows that even though we only consider one initial condition, it works for anything. Okay, moving on here. The other fundamental operation is optimal control for unitary gate operations. So here a gate is represented by a unitary matrix. It's a complex, in general, a complex matrix of size n by n. And again, the goal is to drive any initial state rho 0 to this transformed state, the rho target, which satisfies this formula, V rho 0 dagger. So again, one way of doing it is to span all the different initial states using a basis and make it happen for any element in this basis. But then there was a paper by Christiane Koch and her co-workers back in 2014 that shows that it's actually sufficient to only consider 3 specific initial states. And that is enough to guarantee that this will happen for any linear combination or any initial density matrix. So then the objective function has this form. So now we need to solve Lindblad's equation 3 times. And that to guarantee that the unitary operation is satisfied. So here we have one example. We have a controlled NOT gate, and then it's this small 4x4 unitary matrix. So here we, let's see now. We consider a gate duration of 70 nanoseconds. We use 50 B-splines in our control parameterization. And the carrier waves, they trigger this, excuse me, transition from the 0 to 1 energy levels. So this is 2 coupled qubits. So here we get a final gate error of 0.11%. And on the left here, I show the convergence. So we consider 2 different objective functions. The first one is the Frobenius norm here in purple and in green and in yellow. And the difference between these is that for the purple one, we consider a full basis. And then the green one only consider these 3 bases. And then as pointed out in this paper from Christiane Koch, it's beneficial to weight the different states, and then you get slightly better convergence as shown here with the yellow state, the yellow evolution. We also consider the trace objective function. And in this case, the gradient, even though the final control vector gave a very small infidelity, the gradient never really converges towards zero. It just bounces around. So here to summarize this, the best result, the fastest convergence was when we used the full basis, although that is more expensive than doing just 3 states. So if you have a large parallel machine, you can run all these different cases concurrently on different cores, but if the size of this unitary would be larger, eventually you run out of cores, and it might be beneficial to use these 3 states. So to gain further insight into what's going on here, we actually approximated the Hessian using finite differences at the optimal point. And then we found something very interesting. So here we have about 200 elements in the control vector. So there would be 200 eigenvalues. And it turns out that 15 of them are much larger than the rest. So these are kind of the essential eigenvalues. And then a large portion of the Hessian is almost as eigenvalues very close to zero. So it indicates that the problem is what I would call rank deficient. And with the trace norm, we get a substantial number of eigenvalues that are negative. But this is not the case with the Frobenius norm. There are some that have small negative values, but it's not clear if this is due to the finite difference approximation or if it's real. But it's very interesting. So if I had known the eigenvectors of these 15 substantial eigenvalues, I could have parameterized and found a solution using just 15 basis functions. And there is some theory that it's a little obscure, but it's in this paper by Martin La Rocca that shows that any unitary transformation of size n by n can be accomplished with n squared minus 1 basis vectors or basis functions. So n squared minus 1 in this case happens to be 15, so that seems to agree with this theory. But I find this very interesting. Okay. So Quandary is open source, so if you want to use it to design some other gates, you can do that. And here we have a larger example where we have 4 qubits. And here we implement a generalized swap gate. So it's going to swap the first and last qubit and leaving the intermediate ones unchanged. So this is the truth table here. You see when both of them are 0, then it does nothing. And if the first one is in 0 state and the second one is the 1 state, they are being swapped and so on. So here we apply this technique. We have the optimization history here over on the right using the Frobenius norm. And we see eventually we get down to a small gate infidelity, even though as the problem gets larger, we clearly need more iterations. Right. So here, as the system gets larger, the time, compute time for evaluating each gradient gets to be substantial. So it's in minutes here, and you can see here that this took something like 2,000 minutes. So let's see now, 2,000, so 1,440 minutes, that's 24 hours. So this was a long duration of the calculation, the optimization. So this is something we would like to improve on in the future. So to do that, we have implemented a couple of techniques for distributing the the calculation over an HPC system. So we implemented 3 levels of parallelism using MPI. So the first one is the obvious one. If you have several independent components in the objective function, they can be solved independently in a concurrent manner. And so, for example, when we do a full basis for the gate optimization, then we can solve n squared of these if you have enough cores. If we use the 3 initial conditions, then we can solve the 3 in parallel. So this I will not discuss in more detail than that. But to get further speed up, we have used the PETSc library developed with Argonne to distribute this vectorized density matrix over a parallel machine. And one thing I'd like to emphasize here, that the speed up you get from this type of parallelism, so say it's n squared here, if you have a full basis, they get multiplied by the speed up you can get from here. So they really work together hand in hand. There's also a third, more experimental version type of parallelism. It implements a multigrid-in-time scheme using the XBraid library. But this is still active research, and I will not talk more about that today. So here are some examples, increasing the problem size gradually. So here we have 2 cases. We have n squared here is 65,000 something. That corresponds to 2 to the power of 8 squared. So that would be 8 qubits. And you can imagine that either you have 8 qubits that each have 2 energy levels. You can have 2 qubits, which each have 16 energy levels that give the same size of the problem. And they both require about the same compute time. So here we have the compute time on the the vertical axis, and then the number of cores on the horizontal axis. So you get some speed up, and the amount of speed up you can get depends on the size of the problem. So the largest case we have here has 12 qubits, and here we, by increasing, throwing more and more cores on it, we eventually got to speed up of 328. It's not perfect, but it's substantial. And just to see that, show that we're in the ballpark of what other codes can do on a single core, we ran Qutip on these cases, and it was about the same execution time. However, Qutip does not parallelize, so it doesn't matter. Even using a shared memory platform, it gives about the same execution time if you throw more cores on it. So a slightly more realistic test is to see how long it takes to calculate the gradient of the objective function. And here we exemplify this on a 0-to-1 transfer problem of duration 1 nanosecond. So and here the idea is to do a weak scaling study. So when you increase the number of qubits, the state vector doubles, and that means that the density matrix, the size of the density matrix quadruples. So we throw, when we go from 7 to 8 qubits here, we throw 4 times more cores on it to see how that scales. So for very small problem sizes, there's no benefit to running on several cores, but as you increase the size here, starting at 6 qubits, you see some benefit. And then if we just continue running here on a single core, as the problem gets bigger, we see here, this time here is in minutes. So as I mentioned before, 1440 minutes is 24 hours. So the last dot here actually corresponds to 11 days. And this was actually not done. We extrapolated these last 2 values, but you see that completely undoable to do any kind of optimization, because this optimization will require many evaluations of the gradients to get a converged solution. But using PETSc, we get a much better behavior. We still get a linear growth in the log scale, and there are two reasons for this. The number of time steps scales actually as the number of qubits squared, and also the number of non-zero elements in the system matrix also scales that way. So there's actually, it's not a perfect weak scaling study, but that's in the nature of these quantum systems. So we would like to claim that using this type of parallelism puts optimal control for maybe up to 10 or more qubits into the realm of what's possible. So to finish off here, what we're looking for now is ways to further improve this performance on parallel machines. So right now we're using PETSc, and we treat it as regular matrix vector products to evaluate the right-hand side during the time stepping. But there's a lot of structure in this problem that you ignore by doing so. So what's really needed to evaluate the right-hand side is to contract density matrix times a Hamiltonian that has a very sparse structure. And it's shown here. For the lowering operator, it's really, if you have capital Q subsystems, there's a lot of identity matrices that are used here, placing out the elements in this one-dimensional lowering operator into the big matrix, so to say. So there's a lot of repetition, and once you store it as a big matrix, you lose all the structure. But you can hand code this, and it turns into something looking like a multidimensional finite difference stencil with nearest neighbor and nearest neighbor operation in all the different dimensions. And by doing so for small numbers of coupled systems, we have observed at least a speed up of 2 to 10. So we would like to explore this further. One challenge here is, of course, that if each system only has 2 levels, adding kind of ghost levels to these, that increases the dimension of the whole problem significantly, and it's also going to be a lot of communication to put this on a parallel machine. So these are challenges we're trying to overcome. So in conclusion here, I've told you that designing microwave pulses is a fundamental component in building real-world quantum computers. The code Quandary simulates the time evolution of a given open quantum system. Also, Quandary applies the gradient-based optimization to design control pulses for conditional state preparation. It's also known as the state-to-state problem. And for the unconditional state preparation, which is like the all to a target state problem, or for logical unitary gate realization, which is also includes either a basis or a reduction of 3 specific initial states. And we have demonstrated significant parallel scaling capabilities on HPC platforms with up to more than 1,000 cores. So with that, I think I stop, and I'd be happy to take questions.
Okay, thank you for the interesting talk. Let's thank our speaker virtually here first. Yeah, so I have a quick question here before I open the floor. On the last slide, you had mentioned this that this that the simulation looks like the matrix free solver. You said it's based on tensor contractions. Now, I guess pardon my naivety here, but is there any relations between the tensor network simulators that people typically use for for very specific types of quantum simulations and what you're doing here, or is that just just it just so happens that that the name tensor shows up in both cases?
I think that tensor network is more general, that it can be more complicated things sitting here in the middle. And it can also, I would imagine, be non-unitaries in several parts of the tensor here. I'm not very familiar with what they do with these tensor network calculations, but if I understand correctly, it's done to simulate what a quantum computer does and the whole set of unitary gate operations and how they interact. So I would say that this is a little specialized version of that, simpler, possibly.
I see. Okay. Okay. Any other questions for the speaker?
Something in the chat.
Oh, hi, I have a small question. When you were talking about the scaling on the runtime, you said it's a Q square rather than like Q cube because this one, because what I imagine is that they are all like dominated by the matrix multiplication, and the scaling of that is going to be Q cube rather than square. So why is it square in this case?
Well, the Hamiltonian we have is very sparse. So that it's the number of non-zero element in that matrix, and that happens to be Q squared. So that number comes from the particular form of the Hamiltonian that we assumed. So this is a fully coupled end-to-end coupling term. But if you have more general, if you would have a full Hamiltonian, it would certainly be larger than that, and you probably get a cubed case.
Yeah, so I just have a small follow-up question, like for the small matrices, the speed up can only happen when the number of non-zero density is small. It's like less than 10% or even 1 or 2%. Otherwise, it's gonna be slower than the dense matrices, right?
Than the what? What did you say?
Than the dense matrices, multiplication.
Well, if you don't parallelize, the compute time is going to grow exponentially. So even if you had capital Q cubed, it would be something like this. It would go up a little faster, but it would still be linear in the log scale. So there is definitely benefit to parallelizing it. Does that clarify your question?
Yes, a little bit. Yeah, thank you. Yeah.
Okay. So as I mentioned, this is still under active development. So Stephanie and I and Jonathan, we are looking for collaborations. If you're interested in exploring this, you can download the code from GitHub and start playing around with it. And we'll be happy to talk to you about your particular application that you want to solve.
Yeah, thank you.
I must have been all crystal clear.
Are there any other questions?
I have a question about this plot. So it's not clear what the system architecture you worked with. If you work with different number of nodes which have different number of cores, then do you get similar green curve as you get here, or like how does the system architecture and node core number distribution affects this parallelism?
So this, I'm not sure I understand your question, but I can mention that these timing results were run on a machine called Quartz in Livermore. It's a Intel cluster. So each node has 36 cores. We use 32 of them per node. And then, so if you have 2 to the 12 cores here, that means that you're running on 2 to the 7 nodes, which is 128. So this can be extended to other architectures. It doesn't really matter so much. I mean, we use MPI to communicate between cores that even sit on the same node. It's all due to the internal implementation of the MPI library. So we don't really have to know those details, but of course it relies on having a fast interconnect between the nodes, which usually is the case in a supercomputer.
Yeah, okay, thank you.
I have a quick
We have a
question.
question. Oh, go ahead.
I just put it in the chat. So are there instances where you might be interested in adding constraints on your controls alpha? In your case, the alphas are the coefficients of the basis functions, but are there examples where you might want alpha to either be non-negative or within a range or satisfy other constraints?
Yeah, I actually didn't mention that. Thank you for bringing this up, but we do impose amplitude constraints on these coefficients. So there's like a min and a max value.
Okay.
But I think that one needs, this is the situation we'd like to improve upon. So here it took 1,000 iterations using here PETSc's tau algorithm. And yeah, I would love to see this converge in less than 100 iterations. And there might be ways to add other components to this objective function that are like physics informed to speed up this convergence. Because right now, that seems to be the bottleneck. As we increase the size of the system, we can evaluate the objective function very efficiently on a parallel machine, but it still takes a lot of iterations, and this is like sequential on the machine.
And do you think this is because the step size is very small? You didn't have a step size in your update rule for the quasi-Newton method, but I assume there's a step size. So does the LBFT solver take small steps here? What do you think is causing this?
I think it's the Hessian. So it's rank deficient. And what happens, I think, is all these almost zero eigenvalues is the big subspace of the parameter space that is not well determined. So there are many solutions to each control problem. And depending on how you started, we started with a random initial guess, you might get one of them. But I think that if you could find a way to remove a big chunk of all these zero eigenvalues in the Hessian, I think the convergence would be better.
And is this the Hessian or is it the quasi-Newton approximation to the Hessian? So
well, so here it is not the true Hessian, but we approximated the Hessian by finite difference approximation based on the gradient.
Yeah, no, that's what I meant, because the quasi-Newton approximation doesn't necessarily approximate the Hessian. So that's
yeah. So this is the actual Hessian.
Yeah. You could try regularizing the problem by adding either some form of regularization that makes it positive definite.
Tikhonov regularization, it doesn't seem to do much.
Okay.
But yeah, it's an open question, I think, how to pose this optimization problem to get it to converge faster.
Thank you.
Hi, so I have a question about the accuracy. So you talk about you do the integral for the master equation, in the second order of time interval, right?
Mhm.
My question is that what if the delta t is large, so that you might have to include higher order term?
Yeah,
And
so right. So you have to pick a time step that is small enough. So usually what we do is we estimate this based on the shortest period in the evolution of the Lindblad equation. So you look at the eigenvalues of the Hamiltonian, and you see what is the fastest variation, and then we pick, say, 20 or 40 time steps per shortest period. You run the optimization, you get it to converge, and then you can evaluate the objective function using, say, 80 time steps per period instead. And if you get about the same objective functions, then you're done. Otherwise, you have to improve it further, so you can continue the optimization with a finite time step. But we don't have any estimator built into the time stepper to pick the time step automatically.
sure, I see. Thank you. So I have one more question about the parallelization. So you have 3 levels of parallelization. Are you doing them simultaneously, or each time you just can choose one level of parallelization?
So that is it's done rather automatically. I mean, the same parallelization pattern is used throughout the optimization, each optimization. So it depends on what you're doing and the size of the problem. So you know, for example, if you want to evolve a full basis, you know the size of the basis when you begin, and then you can just run on that number of cores. So that's done at setup.
Okay, I see. Thank you.
Okay, so looks like we are right at 4 o'clock here. So so we'll go ahead and end the seminar for today. Thank you again, Anders, for the talk today. And also, one thing I want to mention is that our next speaker will not be until February 2nd, and that will be Nicole Younger-Halpern. So, please join us again next time, but not in January, in February. So again, let's thank Anders one last time and see you guys in 2 months.
Here, thank you.